Okay, now an important idea in sets is the idea of subsets. So we start with the definition of subset. So we start with A and B, let A and B be sets. If every element of A is also an element of B, then we say that A is a subset of B. And we write it like that, right? A is a subset of B. And the symbol A is not a subset of B means that A is not a subset of B. Okay. What does that really mean when we say that A is not a subset of B? So in English, what it means is that at least one of A's elements is not in B. Okay? A is not a subset of B. Why not? Why is it not a subset? It must be that at least one of A's element is not in B. Because if it would be the case that every one of A's elements is in B as well, then A would be a subset of B. Okay, so if I say that A is not a subset of B, that tells you that at least one of A's elements is not in B. So for example, some examples. So the set containing just 1, 3 is a subset of the set 0, 1, 2, 3. Okay, why is it a subset? Why is the set on the left a subset of the thing on the right? Because every element of this set is also an element of this set. Okay, so therefore this set on the left is a subset of the set on the right. But the set 1, 3 is not a subset of the set 0, 1, 2. Why not? Think about it. Because there is an element here, namely 3, that is not found in the right-hand side. Right? So it is not true that every element on the left is also found on the right. It's not true. So therefore, this is not a subset of that. Okay. What about this? The set 1, 3 is a subset of the set 1, 3. In other words, it's a subset of itself. Is that true? Does that make sense? Well, it does, because every element in here, namely 1 and 3, each of those elements is also over here on the right. Right? Every element that's on the left is also on the right. So therefore, the set on the left is a subset of the set on the right. Okay, so this really shows the same reasoning that I just used right now should work for every set, right? Every set is a subset of itself. How about this? The set 1, 3, is it a subset of the empty set? Well, that should be obvious. The answer is no. Because, for example, there's this element here 1 on the left, which is not an element of the empty set. Right? Moreover, an additional thing, 3 is an element of the set on the left, but it's not an element of the empty set. So it is not the case that every element that's in the set on the left is an element of the empty set. Okay, and therefore, it is not this set here on the left is not a subset of the empty set. On the other hand, the empty set is a subset of the set 1, 3. Why is that the case? Well, the empty set has no elements inside of it, right? Now, it is still true that every element of the empty set is also an element of the set 1, 3. Now, you might say, well, no, there are no elements. Well, okay, but it's still true that every single element of the empty set is an element of the set 1, 3. If you disagree, find a counterexample, right? Prove me wrong, but you can't, right? Because every element in the empty set is an element of set 1, 3, even though the empty set has no elements, right? Okay, so the same reason that I just used should work for every set, right? In other words, the empty set is a subset of every set that you can imagine. Okay, the empty set is a subset of every set. Another example, the set of prime numbers is a subset of the set of natural numbers, right? Because every prime number is a natural number, right? And the prime numbers start from 2, and they're only integers, so every prime number is automatically going to be a natural number. So every element of the set of prime numbers is an element of the set of natural numbers. So therefore, the set of prime numbers is a subset of n. Now, in turn, n is a subset of z, because every natural number is an integer. Now, it happens to be that z includes more elements in addition to the natural numbers, okay? But that's not necessary. That doesn't hurt anything. That, that's just a fact, but it doesn't really matter here. The point is, every natural number is an integer. So every element of n is also an element of z. Therefore, n is a subset of z. Furthermore, z is a subset of q. Every integer can be written as a fraction, right? For example, -5 can be written as -5 divided by 1. So and the same reasoning applies for every integer. Even 0, how can you write 0 as a fraction? Well, that's very easy. 0 divided by anything. 0 divided by 15, except for anything except for 0. But 0 divided by 15 gives you 0. So that's a rational number. So the point is, every integer, every whole number is a rational number. So the set z is a subset of the set q. And in turn, q is a subset of r. Q is a subset of the real numbers. So every rational number is a real number. Okay, so here are 2 facts which I mentioned in the previous slide. So if S is the first fact is, if S is any set, then S is a subset of S. So the point is, in other words, every set is a subset of itself. And why is that the case? Well, again, the definition of subset says that one thing is a subset of something else if everything on the left is also found on the right, right? Well, everything in S is also found in S because it's S. It's the same thing. So every element on the left is also found on the set in the set on the right. So therefore, S is a subset of S. Second fact, which was also brought out in the previous slide, if S is any set you can imagine, then the empty set is going to be a subset of S. And that's because every element of the empty set will automatically be an element of S. Now, there are no elements of the empty set, but that's the point. There's every possible element of the empty set is also an element of S. So, an example, find all the subsets of the set A, B, C. Okay, so this is a new type of thing. We want to find all the subsets of a particular set. Okay, and the book gives us a method for doing it. It's nice to see this method at the beginning, but you shouldn't need to use it once you get used to the concept. But maybe at the beginning it's helpful. But you don't actually need to use it in practice. So the idea the book uses is as follows. We start on the left here. We start with the empty set. Now we want to make subsets of the original set ABC. So a subset might have the letter A in it, and it might not. So we have a question: should we insert A or not? So we start with the empty set. We have one option is we don't insert A. If in that case we're left with the empty set again. Another option is that we do insert A. In that case, we're left with the set containing one element, namely just the letter A. Now, so we're left so far with the empty set and the set just containing A. But now we can also decide whether we should insert B or not, right? Because that's another possible element of a subset. Because we're trying to make subsets of the set A, B, C. So one of those elements of those subsets could be B. So if we take the empty set and we have to decide whether to insert B into that, So we can either not insert it and be left again with the empty set, or we can insert it and be left with the set just containing B. Similarly, we take this set from before, the set just containing A, and again, we can either add B or not. We can insert B or not. If we don't, we're just left with this set. Otherwise, we're left with this new set, A comma B. And now finally, we have to decide, should we insert C into a subset? So we have these four choices from before, these four subsets that we created before, and each of them we can insert C or not. So we're left with these 8 possibilities here on the right, and these 8 possibilities here on the right are all the possible subsets of the set A comma B comma C. Okay, and now but here's another way to write them out. The subsets of A comma of the set A, B, C are, so first of all, the empty set. Okay, or you can write it like this, as in the picture, just 2 curly braces, but either way is correct. So again, we want subsets of the empty of the set ABC. Well, we know the empty set is a subset of every set. So the empty set is certainly going to be a subset of the set ABC. So that's one subset. Then we have subsets of size 1, of cardinality 1, right? So we have the set just containing A is certainly a subset of the set ABC. The set just containing B is certainly a subset of the set ABC, and similarly the set just containing C. So those are sets of whose cardinality is 1. Those are the only 3 subsets of cardinality 1 that we can make in this example. Then we can go on to subsets of size 2. So for that, we can do A with B, or A with C, or B with C. And remember, the order doesn't matter. So it wouldn't make sense to say B comma A because we already have A comma B, right? It wouldn't make sense to say C comma A because we already have A comma C. We're just looking for groupings. We're not looking for orders, because every subset is a set. And remember that in a set, order is insignificant, right? So there's no difference between the set A comma B and the set B comma A. If they were lists, it would be a different story, but they're not. They're sets. Right. So again, it's important to remember a subset is itself a set. And then finally, those are subsets of size 2, and then we can have, there's only one possible subset of size 3 for this example, which is the original set itself, A comma B comma C. Now here's an interesting fact that is somewhat suggested by the tree from the previous slide, but it's, I wouldn't say that the tree proves it in any way, but it's I'm giving to you as a fact. If a finite set has n elements, okay, so meaning assuming it's not an infinite set, okay, because strange things happen when you're dealing with infinite sets, but standard set, a finite set, if it has n elements, n could be any number of elements, then it has 2 to the power of n subsets. So this is a really nice fact to use, because given any set, as long as you know how many elements the set has, you can automatically determine right away how many subsets it will have, meaning how many different possible subsets it will be possible to make using this set. Now, it's suggested by the tree because the idea is that each time you add another option to the subsets, each time you add another possible element to the subsets, the size of the tree doubles, right? You start off with inserting A or not, so you have 2 options. Then when you have a choice to insert B or not, the number of possibilities doubles from 2 to 4. And then when you consider the option of inserting C, the number of possibilities doubles again from 4 to 8. And this gives us 2 to the power of n. But okay, the tree does not prove it. It might be suggestive, it might not be, but this is a fact that you can use, and it's helpful in many of the homework problems. Okay, some examples involving subsets. Okay, and so it's going to, we're going to have to make sure we understand each one of these. So first, the number 1 is an element of this set, right? Why? It's that element right there at the beginning. So that makes sense. Now, however, 1 is not a subset of this set. So why not? Why is it not a subset? Well, the answer is that 1 is not a set. The number 1 is just the number 1. It's a plain 1. It's not a set. In order for something to be a subset of something else, it must be a set, right? So if I want to say that A is a subset of B, A must itself be a set. But here, this 1 is not a set. So therefore, it's definitely not a subset of the set 1 comma the set 1. Okay. Next, the set whose only element is 1 is an element of this set, right? And that's the second element that's listed out here. In addition, the set just containing 1 is a subset of this set. Now, why is that the case? Because every element in this set on the left is also an element in the set on the right. Okay. Now, how about this? This is a set that has a single element, which is a set that has a single element, which is 1, the number 1. This is not an element of the set on the right, right? Because you cannot find this element anywhere in this set. Now, however, this, again, the set whose only element is a set, whose only element is the number 1, is a subset of the set on the right. And that's because you can make, if you take this element here and you put it into a set, you get this. Or in other words, every element of this set, there's only one such element, which is this, right? So this element is also an element here in the set on the right. Okay, next. The set 1, 2, 3 is not an element of the set 1, 2, 3. That's obvious. This thing here, this object here, which is a set, is not found as an element in this set. On the other hand, the set 1, 2, 3 is a subset of the set 1, 2, 3, because every set is a subset of itself. Next, the set of natural numbers is not an element of the set of natural numbers. The set of natural numbers is a subset of the set of natural numbers. The empty set is not an element of the natural numbers because the empty set is a set. It's not a number. It's not a natural number, certainly. It's not a number at all. However, the empty set is a subset of the natural numbers, right? Because the empty set is a subset of every set. Okay, next topic, power sets.